You want to check in with your neighbor, make sure that progress is being made. On 1, 2, and 3, you should be able to identify at least 3 points on those graphs. Yes. You're about done? We done? For one, when I'm setting up the graph, should I make equal quadrants 1, 2, 3, and 4? Should I have everything available? Or should I focus on a particular place?
1 and 2.
Just 1 and 2? Are we good with that? I hope it makes sense that if I want to be able to see the graph well, focus on what we have. Oh, that's frozen there. And would you please go ahead and trace it in front of you with your finger? On the whiteboard in front of you. So it's going to start at the point. If we're going down to up, starts at the point. We're going from down to up. Then the bottom would be 1, 0. And then I think I saw this shape going up like that. And the top point is -1, comma pi. And since I was looking for 3 points, of course, the next one that makes sense would be
0,
0 pi over 2. Pi over 2. Okay. Yeah. Show me the special feature of y equals tan inverse of x. Show me what it has. Other graphs don't. Yeah, it has the horizontal asymptotes at pi over 2 and negative pi over 2. We know that because the inputs for tangent of x are undefined at pi over 2 and negative pi over 2. And we could be reminded on the unit circle back there, can't we? You can see that the vertical asymptotes of just tangent of x would be pi over 2 and negative pi over 2. Just picturing the unit circle. All right, is it back there, Quinn? It looks like it's over there too. Look at that. Negative pi over 2, pi over 2. And would you please go ahead and show me what that graph looks like? Nice. So one of the points I'd be looking for, of course, would be 0, 0. What's another one? Check with your neighbor. What is the other one? So is a pi over 4, 1?
Yeah.
That'd be for tangent, it would be pi over 4, 1, but for tangent inverse, it would be 1 pi over 4. 1 comma pi over 4. And then the other one, of course, is -1, -pi/4. We could see that on the tangent, where tangent of pi/4 is equal to 1. Tangent of -pi/4 is equal to -1. Cosecant of x. I'm going to start by drawing what function? Sine function, but I'm going to make it dashed. I'm just going to refer to it. And remember, cosecant is the what? It's a reciprocal of sine. That's why we start with sine. So those zeros, what happens to them? They become the vertical asymptotes, as the reciprocal of 0 is undefined. From here, can you show me what it looks like? Yeah, we're looking for something like this. Reciprocal of 1 is 1. Reciprocal of anything less than 1 is going to be more than 1. So they touch here and then just come up forever, down, etc., etc. Yeah. Please show me what this function looks like. Are we good that it is v? Because square root of x squared is the same thing as absolute value of x. In my last class, I thought someone said something interesting. How about we just square both sides? Y squared equals x squared. And then no, I squared them. I didn't take the square root. So we have y squared minus x squared equals 0. Do you recognize what that is? Is it a hyperbola? It is a hyperbola, but when it's equal to 0, that is called a degenerate hyperbola, meaning we're left with an x. We just have the top of that x because we started with y equals positive square root of x squared, which I think is an interesting tie to what we've been doing. Not anything I would expect you to know that that's kind of like a degenerate hyperbola. Just know that that's equal to absolute value of x. In other words, if you plug a -5 into this function, output is +5. The only thing that can come out of a square root is a positive number. So yeah, when we plug in -5, -5, we get the same thing. Easy. Cool. So today we're going to continue our limits, discussion of limits. Everything that we've done so far could be on the quiz next time.
Today is also.
Today is also on the quiz, yes. So including today. Last time we talked about limits going to a point, mostly like x goes to 5 from the left, from the right, x goes to 0 from the left to the right. Today we're going to focus on going to infinity, limits to infinity, which is something we've already done. So I'm going to step out of your way as you discuss. Where are we? Why is it the last page right now? What page should we be on? 17 or something? 16. Page 17. Oh, there we go. I wonder how that happened. Okay, so you remember when we studied these? When we studied end behavior. So I'm gonna give you a couple minutes. Well, that first one, do you already see what the limits are? The positive, negative, infinity. Check with your neighbor, make sure that they're clear about what's going on here. Show me the visualization that will help with this. Are we good with this? So in our mind, using this and this. Because of this, right? Do we care about this? We don't care about this. This has something to do with the middle, with some sort of bumps in the middle. We care about what happens when x is going to positive and negative infinity. So all we care about is the dominant term, the leading coefficient. That's why in our mind we have this, so that we can answer the first one. The limit as x goes to infinity of this function is equal to negative infinity. The other way is positive infinity. Rings a bell? Cool. I'll give you some time to work on the rest of these. Have you finished? Make sure you're consulting with your neighbor.
Too modest.
All right. So this one, would you show me what goes into your head before you write the answer for this one? Show me. Yeah, be careful, right? This one is set up to fool you, isn't it?
Yeah.
But you got ahead of that trick. Because we're looking at a leading coefficient that's not in front, it's not written in standard position. So both of these are infinity. Yes. Because x to the fourth. Right, the trick problem.
Yeah, I really.
This one. I need some input from someone here. Nathan, can you help me with this one, please?
Yeah, so arctan is just tan inverse of x.
Okay, exact same thing.
So then I refer to the graph that we drew in the form
How handy.
and so as x approaches infinity, it should be at power 2. It's going to power 2 and then negative power 2 as
Are we good with that? Thank you. Nicely done. This one, sine of x. Let's see. Quinn, did you get these?
There's a problem with sine of x, which is that it never stabilizes.
Exactly.
So for both of them, you have to hit them with DNE.
That's right. Nicely said. You know the lingo too. D N E.
Every math.
All right, good. For a limit to exist, it must approach a specific number. Who'd like to help us with this one? Tell us about how they did it, what they got. Yes, Andrew.
Okay, so I started with the negative infinity version.
Okay.
And I noticed that as x is getting smaller or going closer, get more negative, then the value of e becomes like increasingly like insignificant, like really small. So I said that the limit of x is x is 2.
Can you, before you continue with that, how did you get really small?
It's
Where did that come from?
like a negative exponent is gonna like be smaller than e.
So like negative 100 or something like that.
Yeah.
Same thing as saying 2 minus.
1 over e.
Okay, so that's really tiny, isn't it? Are we good with that? The approach is 2 there. That's some really nice analysis. And it's interesting that you did that first. Okay, keep on going. So x to the. Are you okay with finishing?
Yeah, that was up to that. And then x to the then as x approaches infinity, e is going to become a lot larger. Or that here the e to the x larger. So you're going to get closer to negative.
So you're saying like if we have e to the 1,000, that's huge, and 2
Yeah.
minus. Okay, so we get negative infinity. Are we good? Yeah, that was perfect analysis. Thank you. Did anyone think about this differently? Because also with graphing, you can make that happen. Did anyone think of the graph? You know, e to the x looks like something like this. With transformations, and we're just looking at this, right? Transformations means what do we have to do first? Flip it, right? It's outside the function, and then to up, isn't it? So that horizontal asymptote goes from 0 to y equals 2. So it becomes this. But I think we get the exact same information that you got. But I like what you did because then we don't have to make a graph. We don't have to worry about, did I make a wrong? Did I move to the left instead of up? That was good. Thank you. Yes.
Do you want us to specify that it's 2 from the left?
Oh, good question. I wouldn't, but if you're going to specify, it should be 2 from below. Yeah. And you to put that little negative on it. But definitely you don't have to put it. But if you see it somewhere, please don't be confused by it. ln of absolute value of x. What the heck? Use my language. You could help us with that. Chazzy, you ready for this?
Yeah, I mean, I don't know if it's, I think it could just be infinity for both.
How'd you get that?
Because like the half that's all gonna be positive, so should always be getting like closer to.
Nice. So are you picturing the ln graph by any chance, or you just know that?
I was going off the base.
Okay. Okay. That's good. And what if you have a feel for the ln, which hopefully you do, I hope it makes sense as x is going to infinity, y is also going to infinity slowly, but it's not, there's no horizontal asymptote, so it's going to go up forever. And then the absolute value just makes it so that you're playing in the same numbers. Yeah, it's a reflection over the y-axis. So the input is positive. Because otherwise you can't play like negative numbers into ln functions. Who does that? No one here. Easy. Different levels of easy. Any questions? Okay. Moving on. Well, look at these. Horizontal and oblique asymptotes. I can give you a moment to discuss all 4 of these.
Okay. There's a.
Oh, no, but you have to find.
That would be.
Well, how is it?
I think it's
on the ratio.
Yeah,
So bottom end is bottom.
if it's bottom heavy, it's zero, right? And if it's top heavy, it's.
One of them is why not? These bottom.
If it's bottom heavy, it's white, it's
Oh,
one.
Brandon's expert.
Neither of us would be experts.
No, I'm Simon, Sophia, and Andrew, experts.
Bottom heavy is the horizontal axis. No. Theoretical.
Why do you?
Yeah, they're saying like
Two checking.
I
think it's also.
How do you
Or is it, oh.
Because if it's. Weird, it's too. Me.
Oh,
Did he get him? Are we done?
Almost.
So show me, we got for the first one with two hands. I think you need to show me two hands for this. Right, so 3/2. We know it's 3/2 because
It's the same ratio.
same degree, right? Degree on the same top. So it's neither top heavy nor bottom heavy, it's even. I see what you're saying. So I would take it as a ratio of
So I said,
the coefficients.
look at like zero, right?
In terms of why is this true? Remember, we're plugging in numbers that are huge, so like plugging in 1 billion, this becomes 3 billion and 1 over 2 billion. But it's basically 3 billion divided by 2 billion. Eventually, these smaller terms just kind of fall away in terms of importance. Give you with those two. I'll give you some time to finish these. Has anyone finished all of these? All four? We're not crashing.
Oh, so.
So then we run it, we remember it. Long to pass it, like that.
Oh, I remember. That is.
So what you do synthetic?
Yeah.
Oh. We don't care about these, they're small values.
What? Bottom number, so X follows two.
Speaking on.
Why do next?
Wow.
We're gonna do. Brazil.
I see, okay. This looks. Oh, I love.
Imagine like a heartless.
So.
Extra loop.
Oh, but you can.
Oh,
Are you done?
I don't know.
Me?
Yes.
Yeah. Because this is the top.
Yeah, okay, but you just get rid of.
Can we talk about this one? We ready?
He's the one who makes side X. Let's see how the-
I'm gonna ask you to stop whatever you're working on for right now, and you can get back to it in just a moment. But recognize that this is top heavy by 1 degree, which means if we were to graph it, it would have an oblique or slant asymptote. Should we find out what that asymptote is?
Sure.
We could if we're graphing it, but all we care really is it going up or is it going down? Isn't that all we really care about for these limit problems? We don't care about like where exactly it is. So just like the last one, what I'm gonna do is I'm gonna say, well, x is going to infinity, so some numbers are gonna fall away as x is quite big. Which terms are gonna fall away? Definitely the 1. Definitely the 2. 3x is gonna go, like it, compare it, if you plug in a billion. You know what a billion squared is? Huge. Then you have multiply by 7, so you get 7 billion. Minus just 3 billion, it's insignificant, but even this becomes insignificant compared to this. So you keep the dominant term to the top and the bottom. So this approaches. It's approximately 7x squared over x, which is equal to 7x, which is the slope of the slant asymptote. So all we know now, we have enough. So as x approaches infinity, this function is going to approach infinity. It's approaching. The top is basically 7 times bigger than the top. Than the bottom. Top is 7 times bigger than the bottom. Not 7 times, it's 7x bigger than the bottom. And as x goes to negative infinity, negative infinity. And if you wanted to find the slant asymptote, you would have to use either synthetic division or long division. Or Desmos, I guess. I think synthetic or long. 2 more. Don't fall for the trick. Did you almost fall for it? Well, if you know you fell for it, why fall?
Well, he told me.
No. Yeah,
Yeah. It's so sorry. Like slime.
Yeah.
For limits. You have to divide.
But like, it's not a problem. We used to use 7 square root.
Right. It's about behavior. Not that. Are you done? I'll give you 10 seconds. Can you show me what the asymptote looks like for this? Yeah, we noticed that it's top heavy by 2, which means it's not going to be a slant asymptote, it's going to be parabolic asymptote, which is pretty cool. Okay, which tells us that the limit as x goes infinity, infinity and negative infinity, infinity.
But that could have just been implied because like it's x over x to the 4 and x.
Yeah, right. The small terms fall away, so x, yeah, x squared is the behavior that it's following. Nice. Are we good? Did you get this one?
Yes.
Is top heavy, bottom heavy, equal?
It's equal.
It's equal, isn't it? Which means there is
Heavy velvet the trick.
horizontal asymptote at -5/3. Of course, it's important to remember that if it is bottom heavy, then the limit as x goes to infinity and negative infinity would be 0. Sure. Any approaches are- So far, so good. Nothing super new, I think, just kind of a rehash of what we've done before. This is a little different. Radical functions. Okay, well, these work the same. As we're plugging in values to negative infinity, some of these terms are going to fall away, specifically the 4 on the bottom and the -3 on top. So we have 5 and 15x squared, square root of all that over x. And again, I hope that makes sense. You plug in -1,billion. Square that, multiply by 15, subtracting by 3 won't make much of a difference in the actual value of that number. 1,000,000 plus 4 is basically 1,000,000,000. So just go into that. Go ahead and continue. See if we can figure out what is the limit. There's a little bit of a twist here, so be careful. Is this top heavy?
Because when you get rid of the bottom half. But I just like was thinking that we're at 15, it's like over -1,000,000. Yeah. You get, oh yeah, you get 3 acres. It's red. Oh.
What happens?
No idea. Yes.
Should I continue together?
I think the limit becomes 15.
Something like that.
Something like that.
Yeah,
Yeah, I think.
pretty good guess. I hope this makes sense. It's gonna be square root of 17 times square root of x squared over x. Do you know what the square root of x squared is? Is it x? The value of x. So we're doing the limit as x goes to -infinity. Let's think about this. Now, they don't really cancel exactly. But let's say we're plugging -1,billion. What's gonna happen?
It's could be about one.
It's
What do you mean?
It's negative square root.
Negative square root of 15.
So.
That bottom stays negative. Top. It's the same value, but opposite. So the quantities kind of cancel. But you're left with a negative number. Right, tricky. Do you like that? Oh, not -1, negative. No? You don't like it?
No.
You love it. I see. Now, if x are going to positive infinity,
It would be positive if through 15.
then we wouldn't have the same problem here. We'd just have positive square root of 15. And if x is going to positive infinity, then we wouldn't have the opposite values. It would just cancel neatly. But negative, this becomes whatever negative values in there. If it's positive, that stays negative. They cancel out, leaving that negative root 15. That was a little different, wasn't it? We haven't done that before. Excitement. Do you have any questions? Perhaps your question is, may we have another? The answer is yes, you can have 2 more. There you go. Enjoy.
Like, go ahead and just be like that. We have to look together. Yeah.
Oh. Did you get them? Check with your neighbor as you go. I'll be calling on 2 people. Help me out with these.
No, the 9.
Yes. Hey, it's the same format. Hey. What? Is it negative for? Yeah, well, it doesn't look like. Damn. Stop reading.
Are you done?
Yeah, it's data.
Both on Nola and Henry today. Interesting.
I'll take over.
Will you? We'll see what Destiny has to say about it. So close. Andrew, can you help me with this, please?
So I saw the 4 and the 9 all the way,
Okay.
so it's negative. So it's negative x over √5 times absolute value x. And then you can plug in infinity,
Okay.
so you get negative infinity over √5 times infinity. And then can't the infinity cancel. So
Okay.
it's negative 1 over 5. Well, it's negative 5 over 5.
Is either one okay? Are we good with this? Nice. I understand the inclination to plug in infinity, but and it works, but as a teacher, you notice I always say like a billion. Infinity is an idea, so when plugging something in, it should be a number. But it gets you the same place, ultimately. We're probably plugging in a huge number. A billion is kind of the same thing as infinity.
What about a trillion?
Ooh, a trillion is more than that. Good point. This one, did you get this already? Let's see what happened here. Oh, shoot. Oh, Sabrina, help me with this one, please. What's that? Well, we are going to infinity, so I think some of these terms are going to say adios. Which ones do you think are going to go away? I'm sorry, I'm having a hard time hearing you. Exactly. So it becomes this. Okay. And then what can we do with this? √6. Pardon? Times the root x to the 4th. Is that what you said? Okay. Over x squared. Yeah, what is the square root of x to the 4th?
X squared.
Is it x squared? Should we put on absolute value?
Yeah, it's just, yeah. Say. I'm sorry.
Okay. So now what happens? This is going to negative infinity, right? So is anything going to be negative in here once you start plugging in huge negative values? No. So what's going to happen with these 2 quantities? Cancel. Leaving. Square root of 6. Are we good with that? Nicely done. Thank you. Do we need those absolute value signs around x squared? Yeah, absolute value. What's that? It's going to be positive anyway. Absolute value is there to ensure that the output of that quantity is positive. It's already positive, so there's no need to put it there, even though it's not wrong. It's not necessary. Just in case. Doesn't hurt.
Wait, what if it was like x this big? numbers that you would need.
Yeah, for sure. Would we? X to the sixth? Maybe X to the fifth. Oh, but I see X to the sixth. Yeah, it gets difficult. Yeah. Andrew,
So the limits when we go into infinity or negative infinity, if like the x term does not have an exponent,
Mm.
then we can assume it like falls away.
well, only the dominant term stays. Only the dominant term stays. So what's that? For top and the bottom, exactly. They have to battle up against each other. So between these two, this one just goes. These two, this one just goes. Even if it's at 3x. We go. Yes. Yes, from the top of the bottom, you just choose just the most dominant, or the highest degree. The term with the highest degree. And that's what determines the end behavior. Ultimately, no matter what's happening in the middle, it's that leading coefficient takes over to say where it's going to go. It's dominant. It has control of the situation. Before we continue, I'm going to give you a little bit of time to discuss things we've talked about or to zone out. We'll continue again at 2:35.
Recording in progress.
I do want to remind you that during the breaks, I prefer that you stay here. So if you need to go, you of course may do what you need to do, but it's just a little strange when like 7 people walk up. But maybe everyone needs to do something, and that's fine. Okay, some basic limit properties. Next year, these will be referred to as limit laws. So remember, limits, we're looking for what happens to y as x is doing something, right? The very first time you look at this, y, as x is approaching such and such, y is approaching such and such. Does that sound like your understanding of limits?
Yeah.
And up until now, we've had very specific functions, but it's not always going to be that way. And in that case, what we have is some limit laws, which are pretty intuitive. It doesn't look like it when you look at the book here, but it's actually not too bad. All this is, oh, I froze the screen, didn't I? Okay, all this is saying that first one is if you have a limit of a function plus another function, that's equal to the limit of the first function plus the limit of the second function. It's like the distributive property. But distributive property holds some multiplication, but it looks just the same. See what I like to keep it for me back. It's not, I have no idea. Not a question. Okay, so same thing with subtraction. If you have a constant multiplier as a fraction function, and you take the limit of that, you can factor out the constant multiplier. If you have a limit of product of two different functions, you take just the limit of three different functions. Limit of function over a function, then that's the limit of function of the limit. Right, it's hopefully it's very intuitive how we go from the left side to the right side. This warning that you see in your book right here, that's be careful, should be on the number 5. That the limit for g of x should not be equal to 0. You see why that is, don't you? Yeah, it should be on 5. Yeah, they messed up. It's fine. It's fine if this one's 0, but number 4 is fine. For 5, you just can't divide by 0. So you'd have to find some other way to do it. And 6 and 7, I hope that those also make sense. I can take the power and put on the outside of the limit, take the radical, put on the outside of the limit. The assumption that we're making here is if n happens to be even, is that the limit on the inside would have to be positive. Okay, so I'm going to skip and do one example. We're going to skip over this page just briefly. We'll come right back to it. So here we go. We're looking for the limit of this craziness as x goes to infinity. And we have no idea what these functions look like, but instructions do tell us a few things about each one of them. So what do? We rewrite this using the basic properties of limits or the limit laws. Specifically, it's going to be limit as x approaches infinity of f of x plus, you see what's gonna come next?
3 times limit g of x.
Yeah, 3 times the limit as x approaches 0 of v of x. Is this a difficult problem to do? No, they gave us all the information we need. So go ahead and finish this up. Make sure your neighbor was able to get the same thing you did. It's weird.
Not that good fun.
If you got on a count of 3, I'd like to hear it. 1, 2, 3.
Negative.
Negative 12. Are we good? We know this first part is, what is it? 3 plus 3 times -5 is just -12. That's it. So if you look through these, and we're not gonna do these now, but when you do these, it's gonna be the same kind of thing. You just follow those basic properties of limits. Going back to page 20. He's about to get a little bit of abstract here. Okay, I'm gonna ignore what this is saying right here. We'll do this intuitively. So here, they give us this information. Can you picture that? Can you picture this right now? We don't know what the function looks like, but we know that that way, the y values are getting close to that x-axis. Yes?
Yes.
I want you to take a moment to think through this. I want you to notice that this function is the same as this function. But they're both f. So this is f of 1 over x. And how you think about this, see if you can make any sense of that. It's weird.
Well, where do you know? No, there's just a couple total levels came in. The robotic piece that they like TV back. It's just the same. It's that you need back. And it was.
Should we talk about it?
Yeah.
Yeah, let's go back and figure out what this is. This is very basic of things. We have a function f, and this is telling us to put in particular values of x, isn't it? It's telling us to put in values of x that are hugely negative. And when we put those values into this function, the outputs get closer and closer to 0. It's not, it may be equal to 0, but they approach 0 for sure. In this case, this problem is telling us to put in values that are very close to 0 from the left. But notice they don't go directly into the function, do they? It's kind of a pit stop. Before that number goes into the function, it has to go into a different function, namely 1 over x. Like if I were plugging in 2, then the output would become 1/2, and that 1/2 would then go into the function. You see that kind of 2 steps are happening as opposed to the 1 step in the first one. If I were to plug in a 5, I don't know why I would plug into 5, but if I were to plug into 5, first thing that would happen is that 5 would become 1/5, and then that 1/5 would go into the function. So the values that we're plugging in are very close to 0 from the left. Numbers like negative, let's say 1/1000. What happens if you plug in -1/1000? It becomes a -1000, doesn't it? And f of -1000, what do you think is true about that?
It's close to 0.
Close to 0, isn't it? How about if we got even closer to 0, like -1/1,000,000? What happens when you plug that into 1 over x? Because -1,000,000, what do you think is true about f of -1,000,000?
Very close to 0.
You sure?
It's closer. Because we like in larger numbers it goes.
Yeah, it's telling us. So if we plug in larger numbers, the function is headed to 0. So that's why the answer for this one is 0. These ultimately say the same thing. Take a moment to discuss that with your neighbor and then see what you could do with example 6.
Very crazy.
Wait, am I true? One,
Yeah. Maybe it's like. Don't you just like find right to the zeros if you don't want to do there? Just. I guess that that's the GIS. You don't need to just say no. No, oh, so it gets bigger. This one gets bigger. Oh. I really don't know which one. What? No, I'm saying, I don't think we understand. They're going with like negative 1/1. So they're trying to this. You plug in negative 1,000. No. Given that. Plug negative 1,000. Yeah. No, you plug in a negative. Plug it in or. Yeah, that's not right. Zero from the line. Right, and then you have one, and then you have one. X. We're thinking the same thing. Well, there's always one of the anything. We get it.
Yeah, get it?
See, that's easier to tell that it's gonna be 0.
Okay. So hopefully you got a productive discussion. Hey, Brent, do you have a question?
I'm still a little confused about the top. I get the bottom.
Okay, oh, you get this one, but this one was confusing?
Yeah,
Okay,
so it's approaching 0 from the left, that means negative 0.00.
yeah, I'm gonna make a little graph of y equals 1/x, so. Maybe we could use that as reference. Yeah, so we're plugging in negative values into just this function. First.
So why is
Because first we plug it into here, and there's kind of an intermediary step before it goes into the function. Like if I plug in this number, it's gonna get hugely close to 0, it's gonna be even bigger negative. So this number is becoming more and more negative. So when that number becomes more and more negative, the limit is 0.
It's just
all the same thing?
It's the same function ultimately. This one you're playing in values of x directly. Here the x goes into a function and the outputs of that little function go into this function.
It makes it 0.
Makes
No,
sense?
no, no, I think it's like,
Yeah.
because it's getting like closer to negative infinity for the right. And because for the left one, it says, as it gets closer to negative infinity.
Oh, I understand.
Yeah. Yes, the same thing. Yes, this compared with this. Same thing. Thank you for helping me clarify that. And you said you have some insight into this one?
Why is it
I-
infinity?
Is it infinity?
Me and my partner.
Are we like moving that in?
Yeah. No, we're checking to see what.
Think about it. What the limit is.
It's negative 5,000. Look at it.
Yeah, that-
You know how it goes negative, that's small.
Right.
And then look at the left one.
Yeah,
And
and
then it's
you have
going to
it.
negative 2. It's going to 0.
Oh,
It's first one.
What is what we got.
Yeah, it's in the same.
But that's what. No, he knows you have to write. Because it's the same function.
And that's what you read.
Because both with Vinny, it's in. Yeah, so then you have to go back.
Controversy.
Both of them.
Okay, so I'm gonna talk you through this one. This case. X is coming from the right of 0, so I hope it makes sense. This is all we need. And remember, in this case, there's a first stop before it goes into g of x. What kind of function is it? We have a function before another one, composite function. So in this case, these guys are going to cosecant of x, which is why I put it here. What happens when I plug in very small values of x here? It's huge, going to infinity. So once I plug in those numbers into this function, it's gonna spit out numbers that are going to infinity, just like.
See, I get it.
That's why the answer is infinity, because it's ultimately say the same thing. Right? It's crazy.
I get it.
Brandon, that was a nice aha moment. That was nice. That feels good. I wish that for everybody. Andrew.
There's a lot.
He asked them as well.
Is that for you to find the limit of this?
Actually.
But isn't it already?
No, this is given, but we have to use our logic to make sure it's the same thing. It's showing you that this could be expressed in a more complicated way, more analytical.
So we need to prove that that's true.
Yeah, well, we have to analyze. Understand is that why values are going to pop. Just like these are going to pop.
That's the right form.
Okay. I'm gonna be posting this if you want to take another look at it, of course. We do have another problem we have to work on before I give you some time to work on the assignment. This one. You may be tempted to say that this limit is equal to 0. Because like making things go away like before, but it's not. That only works when it's a ratio. So for this one, like if I were to plug in 1 billion, yeah, billion squared plus is that
8 billion.
do I care about this?
No.
For this one, I do ratios that for this one, it might be substitute. So I need to analyze this a different way. And to do this, I'm going to introduce this as a fraction over 1. And I'm not going to square the top and bottom because that is not a thing. Yeah.
Because put it down on the bottom,
But what's down on the bottom?
you're gonna make it like x squared plus 8x minus 3 to the power of -1/2.
Oh, that's an interesting idea. I wish I could, but that minus sign is there. Hudson, you have a question or idea? Could we multiply by conjugates? As long as you do it on the top and the bottom, and I think that's a great idea. I'm not gonna actually, you imagine, do you see what the conjugate is?
Yes.
I'm gonna be a little bit lazy and just write conjugate, top and bottom. And let's see if you can work that out. Nice, Hudson.
Is it in 90? We don't know.
That's okay.
So
You know,
yes.
it's a conjugate. Expert.
It's. Which one's this? It's,
Seven, eight.
What's the conjugate of A plus B?
A minus.
There you go. There you go. It's hard to say, was it?
We really have to like multiply it all out.
Yes. That's the point. You can use them multiply.
Oh, yeah, because.
Wait.
You getting anything? Some stuff, okay.
I don't know if I want.
Better than nothing.
I don't know if I wanted, but I'm getting something. No, we can do it.
So top becomes just x squared plus 8x minus 3 minus x squared. Bottom, I am gonna write the conjugate here. X squared plus 8x minus 3 minus x, oh, plus x, excuse me. Take the limit as x goes to infinity. What happens now?
The X squared leaf.
The x, yeah, say adios to the x squares on top. And now? Yeah, let's leave only the dominant term, so 8x over. In the square root, I'm going to keep x squared and the x. It's not of a lesser degree than the radical, is it? So I keep it. So you see what the answer is? I got rid of these because these are lesser degree of this. But square root of x squared is x. So I'm not going to get rid of this because they're the same degree. So x stays.
But wait,
What's the absolute value that?
Is it 4?
So 8x over
It's 8 over 2, so.
2x. Is that right? So it's equal to 4. Dun, dun, dun. Woo. Yes, Chazzy.
So does that value like really not like, let's say if it was approaching negative infinity, then would you have like the absolute value plus x? Would you be able to like combine?
Oh, that'd be so awkward if we're going to negative infinity. Because then you have a billion plus negative a billion.
To 0.
Yeah, you have
Oh.
undefined denominator. Yeah, I don't know if we could do that one. That'd be interesting to look at. Okay, so you have just a couple minutes to work on your homework. Just so you know, the homework is no longer online. Starting today. I know. Paper. It's right here. This, you already did the first
Oh my God.
one. Oh my gosh. The answers are on the hub. It's 3 pages. Is it for practice? Yeah. I'll be checking it visually. Rihanna, I'm so sorry to hear that it's not been working.
Bro, why?
I did. I was actually reading about this since algebra.
Wow.
What?
Well,
It definitely has its problems.
Bring back my legend.
Is it what?
You have to use limit law.
Yeah.
Nathan, I'm sorry it's been so long since you were called on. That's too long.
No, I was like, you haven't called on me in like
Since February.
Oh, yeah, February.
For what?
The last
I
month.
feel like-
It's been 3 months to get on
I swear it was like the top of.
feel like this would all make sense from the previous. Oh, yeah.
Well.
We're out of there. I don't like to work harder. We love that. Got a great books. Very strong. Well, everyone likes.
I was in one grade.
You're really good.